A new era of cosmic exploration has dawned. But it's not happening in the cold vacuum of space. It's happening inside our most powerful supercomputers. Scientists are building a digital twin of our home galaxy, the Milky Way. A virtual, evolving simulation that promises to unlock the deepest secrets of how our galaxy and we came to be. And the key to building this universe in a box is artificial intelligence. For thousands of years, we've looked up at that faint, shimmering band of light across the night sky, the Milky Way. But trying to understand its true shape from our position inside it is like trying to map an entire city while looking out of a single ground-level window. Our view is blocked by colossal clouds of dust and gas. But that's all starting to change. The quest to map our galaxy is a fascinating story. It really began in 1610, when Galileo pointed his telescope at that hazy band and saw what it truly was: countless individual stars. But the first real map attempt came from William and Caroline Herschel in 1785. They painstakingly counted stars in over 600 different regions of the sky, assuming that where they saw more stars, the galaxy stretched further out. Their map showed a flattened blob with our solar system right near the center. It was a heroic effort, but it was wrong. They had no idea that interstellar dust was hiding the galaxy's true, brilliant center, making it seem like we were in the middle of everything. The next big question came in the 19th century. Astronomers saw beautiful spiral shapes in their telescopes. Were these spiral nebulae part of our Milky Way? Or were they entire island universes on their own, far, far away? This sparked one of astronomy's most famous arguments, the Great Debate of 1920. The key to solving this puzzle came from an unlikely source: a group of women at Harvard known as hired to do the meticulous work of cataloging stellar data. One of them, Henrietta Swan Leavitt, made a discovery that changed everything. She was studying stars that pulsate, getting brighter and dimmer in a regular rhythm, called Cepheid variables. In 1912, she found a precise link. The longer it took for a star to pulse, the brighter it truly was. This was revolutionary. It gave astronomers a standard candle. If you know how bright something really is, you can figure out how far away it is just by seeing how dim it appears from Earth. Henrietta Leavitt had just handed science a cosmic yardstick. Astronomer Harlow Shapley immediately used this yardstick to measure distances to dense clusters of stars orbiting the Milky Way. He noticed they weren't centered on us, but on a point tens of thousands of light years away. His conclusion was radical. The Milky Way was much, much larger than anyone thought, and we were nowhere near the center. We were living in the galactic suburbs. This brings us back to the Great Debate. Shapley argued for his giant Milky Way, claiming the spiral nebulae were just gas clouds inside it. His opponent, Heber Curtis, argued for a smaller Milky Way, and that the spirals were distant, independent galaxies. The debate was finally settled, a few years later, by Edwin Hubble. Using the most powerful telescope of the time, he found one of Leavitt's Cepheid variable stars inside the Andromeda Nebula. He did the math. Andromeda was nearly 1 million light-years away, far outside even Shapley's gigantic Milky Way. The universe changed in that moment. The spiral nebula were galaxies. Our Milky Way wasn't the entire cosmos, but just one of countless billions. It was a humbling and mind-expanding revelation. In the century since, radio telescopes peered through the dust to reveal our galaxy's spiral arms, and infrared and X-ray telescopes added even more detail. But a truly complete, high-fidelity model remained out of reach. And that brings us to the modern challenge, which is twofold: a flood of data and an ocean of complexity. Modern surveys like the European Space Agency's Gaia mission are creating the most precise 3D map of our galaxy ever. Gaia is tracking the positions and movements of nearly 2 billion stars, making trillions of individual observations. And looking ahead, The Square Kilometer Array, or SKA, will generate a data tsunami measured in petabytes per day, dwarfing the data rates of the entire global internet. No team of humans could ever sift through all of that. The second challenge is the physics. A galaxy is a living, breathing system. To simulate it, you have to account for the pull of gravity, the flow of interstellar gas, the birth and death of stars, violent supernova explosions, and the mysterious dark matter that holds it all together. The real killer is the timescale. The galaxy swirls over billions of years, but a single supernova explodes in an instant. To capture that fast event, a traditional simulation has to take incredibly tiny time steps, which slows the whole process down to a crawl. Simulating the entire Milky Way, star by star, would take decades, even on the world's fastest supercomputers. It was a computational brick wall. This is where the digital twin, powered by AI, smashes through that wall. The term digital twin comes from NASA, who used physical simulators on Earth to troubleshoot the Apollo 13 crisis in space. A modern digital twin is a virtual model of a physical system, a living replica, constantly updated with real-world data. But how do you build one for the entire Milky Way? A galactic digital twin is a comprehensive simulation built on the laws of physics, but constantly fed and corrected by real data from telescopes like Gaia. It's a virtual laboratory where astronomers can run impossible experiments. They can rewind time to watch our galaxy form through violent mergers, or fast forward to see its eventual collision with Andromeda. They can even tweak the laws of physics, changing the properties of dark matter, for example, to see which version of reality best matches our own. But as we said, this has always been computationally impossible. Until now. The key that finally unlocked this is artificial intelligence. AI is already a superstar in astronomy. AI algorithms sift through telescope data to classify galaxies with 98% accuracy. They hunt for exoplanets by finding the telltale tiny dips in starlight, which led to the discovery of a solar system with as many planets as our own. But their most groundbreaking role is in accelerating these impossible simulations. In a landmark achievement, a team of researchers from Japan and Spain announced the first-ever simulation of the Milky Way that tracks over 100 billion individual stars. They cracked the supernova problem with an ingenious AI solution. They developed a specialized AI and trained it on thousands of high-resolution simulations of individual supernova explosions. The AI essentially became an expert on the physics of exploding stars. Now, when they run their main galaxy simulation, they can use large, efficient time steps. When a star is scheduled to go supernova in the model, instead of grinding the entire simulation to a halt, they just hand the problem off to the AI. The AI quickly and accurately calculates the effects of the explosion on the surrounding gas and feeds the result back into the main simulation, which keeps on chugging. The results are breathtaking. This AI-assisted method can simulate the galaxy with 100 times more stars than ever before, and it runs over 100 times faster. A simulation that would have taken 315 hours now takes less than 3. A simulation spanning 1 billion years of cosmic history, once an impossible dream estimated to take 36 years of real time, could now be completed in about 4 months. This is a fundamental shift. AI is no longer just a pattern finder. It's a partner in scientific discovery. Of course, this effort requires a union of incredible tools. On one side, you have the data gatherers, the Gaia spacecraft, our master galactic cartographer, and the upcoming Square Kilometer Array, which will map the raw fuel for stars across the cosmos. On the other side, you have the digital forges, supercomputers like Japan's Fugaku, one of the most powerful machines on Earth. The simulation ran on nearly 150,000 of its nodes at once. It's the combination of this brute force hardware with the elegant efficiency of AI software that makes the digital twin possible. The road ahead is still challenging. The physics models need to be constantly refined. The simulations are still incredibly expensive, and we need to ensure AI models aren't black boxes that give us answers without explaining how they got them. But the potential is immense. This creates a powerful cycle of discovery. Telescopes provide data to feed the simulation. The simulation makes new predictions, and new telescopes can then test those predictions. It's a synergy between the real and the virtual that will help us answer our deepest questions. How did the Milky Way's beautiful spiral arms form? What is the violent history of our galaxy's mergers? How were the elements necessary for life spread throughout the cosmos? And what is the true nature of the dark matter that sculpts everything we see? We stand at a remarkable moment. For millennia, we have looked up, trying to piece together the story of our galaxy from faint, ancient light. Now, we are bringing the galaxy down to Earth, recreating its awesome complexity inside a machine. By teaching an artificial intelligence to simulate the cosmos, we are building a mirror to the Milky Way. And in its reflection, we hope to see not just the history of the stars, but the story of ourselves,